When you tell someone the natural numbers are real, you can show them the phone you have in your hand. That is quantity 1. To prove that rational numbers exist, you can divide an orange into two halves. To show them the irrational numbers, you can always point towards a circle or a triangle. But if someone ever tells you that imaginary numbers are real, ask them to show you something that contains imaginary numbers. In reality, you will never encounter imaginary numbers in the real world.
Like everyone else, I have long wondered about the intuition behind complex numbers. For example, what is the role of a number as square root of -1? What sets it apart from other impossible numbers? For example, absolute value of a number which is equal to -1. The initial question might have come into my mind from the way I cut apple slices for my kids. For example, I just cut it like this and a straight line from this, which resembles y equals mod x. As opposed to me, my wife cuts it in a perfectly quadratic fashion. The next question was, why is square root -1 a rotation by 90 degree in a 2D plane? A square root and a rotation do not seem to be linked at all. The final question was, is it possible to make sense out of a number like e raised to power j theta, which is with the values plugged in comes out to be this. This is a question I will not answer in this video, but that is available in the original article. I will give the link below that this video is made from. So what do I do when I have to find out something about mathematics? I open maths textbooks. When I did the same for complex numbers, here is what I found. A complex number is an ordered pair AB of real numbers. Ordered means that AB and BA are regarded as distinct if A is not equal to B. This was followed by properties of the complex number, addition, multiplication rules, and so on. This reminded me of a quote by Georges Clemenceau: war is too serious a matter to entrust to military men. I humbly want to modify it as mathematics is too interesting a subject to entrust to mathematicians. Why? Not because they know less, but precisely because they know more. When you know more about a subject, it becomes very difficult to look at those things from a beginner's viewpoint. My next step: online tutorials on Google. They have never disappointed me in this regard. Always good writings and videos are available. Let's assume some number I exists where I square equals -1. This is what is written in a very popular maths blog. Or I is a root to the equation x square plus 1 equals 0 from a channel on YouTube, or history of quadratic and cubic equations, another channel on YouTube. But none of this tells us where complex numbers came from. That was what I was searching. So I set out to find the answer. Before I do that, I will mention something they all converge on. That is, just like a number 1 is on the right of a real line and -1 on the left side, the number I is perpendicular to the real line, and hence I can be thought of as a rotation of 90 degree from the number 1. This perpendicular plane was hidden from the view of ordinary people, and only pioneers of mathematics were able to discover that. As we will see now, there is more to this idea than meets the eye.
As this does not answer none of our initial questions. Why square root of -1? Why not a number like absolute value of k equals -1? Why is I a rotation of 90 degree in a 2? And is it possible to make sense out of a number like e raised to power j theta? Again, I will not answer the third question in this video, and it has been covered in the article.
For this purpose, we see where all the numbers started. For the early mathematicians of agricultural societies, it was important to relate a symbol to an object, a physical object, which they can see and touch. For example, apples in an orchard. So we have 1, 2, 3, 4, and so on. Whole numbers are the natural numbers along with the number 0. Although ancient humans precisely knew what nothing meant, it was difficult for them to put that idea into a number. It was probably first done in India. There were different independent developments in different parts of the world, but probably first this number was invented in India, as nothingness or emptiness had deep roots in Indian philosophy. Dividing anything into several parts then requires fractions. That's where rational numbers come into play, where an agricultural yield can be divided into a farmer's own household and the government. Rational numbers are characterized by infinitely repeating digits. For example, 6 in this case, or zeros in other fractions. Irrational numbers came as quite a surprise because it was difficult to imagine infinitely non repeating digits after the decimal place. Pythagoreans believed that all numbers could be represented as rational numbers. Legend has it that a student of Pythagoras named Hippasus was trying to represent square root 2 as a fraction, and failure to do so led him to the discovery of irrational numbers, for which he was drowned as a punishment from God. Irrational numbers can be associated with objects, physical objects out there, such as the hypotenuse of a triangle, the circumference of a circle, which has a pi in it, and so on. There are far more irrational numbers as compared to the rational numbers because there are 10 possibilities as opposed to 1 for each place after the decimal. So we say that irrational numbers fill the gigantic holes on the real line left by the rational numbers. These irrational numbers filling the space between rational numbers is like filling water into an ice cube tray. The union of rational and irrational numbers forms the positive real line. You have noticed the absence of negative numbers in the left half here. This was deliberately done as negative numbers are in a league of their own. To give you an idea of how revolutionary they were, Western mathematicians generally accepted the idea of negative numbers around the 19th century, although they were being used by Chinese mathematicians before 200 BC. Interestingly, just like the concept of zero might have a link to the idea of nothingness in Indian philosophy, historian Malzov says that the principle of duality, which is two-sidedness of nature or yin and yang, in the Chinese philosophy might have made it easier for the Chinese to accept the idea of negative numbers. Now we arrive at a time in history when everyday transactions are getting recorded in mathematical symbols instead of words in a language. For example, gaining any possession pushes us further to the right side of the real number line. However, for every path we traverse in life, we must keep the track of our reverse journey. Common sense dictates that our loss should pull the account back towards the left side. These then become the familiar addition and subtraction operations. Standing on a particular positive number x, such a process gives rise to the following four scenarios. So x plus a smaller number equals a positive number, x plus a larger number equals a positive number, x minus a smaller number, a positive number, but x minus a number larger than x, what should we do with this? This asymmetry in the process is a corner case, and corner cases usually lead to new discoveries. To cater for this, a subtraction operation pulls back a number beyond zero, and a negative sign is placed on the result. So, negative numbers were established as simple counterparts to positive real numbers on the same axis. Negative numbers initially caused confusion to the mathematicians since having less than nothing seemed absurd. Nevertheless, the idea was nicely integrated into mathematics by representing it as opposite and fusing it with direction. From your viewpoint, you owe me minus 4 oranges if I owe you plus 4 oranges. Or starting from my home, for example, my journey is plus 3 kilometer if the direction is towards east, while it is minus 3 kilometer if the direction is towards west. This completed the real line. While the positive x-axis was asymmetric as we saw here, the introduction of negative numbers made the x-axis symmetric again. The most important point is that the membership of the real club is now closed. No new entries are allowed because we have exhausted all the possibilities for numbers encountered in real life. That is why I'm convinced that the name imaginary given to the imaginary part of the complex numbers was completely appropriate, although many people use the expression unfortunate for this naming convention.
Gradually, people discovered that the mathematics was the language of the universe, and many phenomena encountered in daily life can be translated into numbers and equations. For instance, a genius handyman of old days could predict his income ahead of time by incorporating his fixed costs with a chosen daily rate and put them into an equation like y equals mx plus c. This process gradually paved way to more advanced relations, such as polynomials. An example of which is y equals x cubed minus 5x square minus 4x plus 6. The simplest example of a polynomial is a quadratic relation. For example, if we throw an object into the air, we can calculate the time it would take to hit the ground. Since gravity imparts an acceleration to the object, and acceleration is the rate of change of velocity, which itself is the rate of change of distance, the resultant equation is quadratic in time. The interesting thing here is that the multiplication itself is actually symmetric. Plus plus equals plus, minus minus equals plus minus equals minus, and minus plus equals minus. However, when it comes to the powers of a real number in the polynomial functions, there is an asymmetry in the result with more positive than negative results. For example, for even powers, we have all the positive results. But for an odd power, we have a positive result for a positive number and a negative result for the negative number. In summary, all even powers produce positive results even for negative numbers, while odd powers maintain the original sign. This asymmetry is similar to what led to the discovery of negative numbers. Let us explore this further with the help of the graphs of y equals x raised to power n, which is drawn here for x raised to power 0, x raised to power 1, x raised to power 2, and x raised to power 3. Observe here that quadrant 1 is taken by positive y values for positive x values. Quadrant 2 is occupied by positive y values for negative x values. Quadrant 3 for negative y values for negative x values. However, quadrant 4 is empty and we have no negative y values for positive x values. This is summarized in this table. Why did I draw these two ellipses here? For positive x, all even powers of x lie in quadrant 1 and cross through the point plus 1 plus 1. On the other hand, for negative x, all even powers of x lie in quadrant 2 and cross through the point minus 1 plus 1. While all odd powers of x lie in quadrant 3 and cross through the point minus 1 minus 1. In other words, there is an oscillation between plus 1 and minus 1 in values of y at x equals minus 1. Something really important to note here is that despite the asymmetry in y-axis arising from integer powers of x, we now have a real line on x-axis and a real line on y-axis. But there is a very important difference between them. The x-axis real line reflects our observations from real life as we saw in the symmetric x-axis like natural numbers, whole numbers, rational numbers, and so on, while the y-axis real line arises from operations on x-axis real. What are the implications of this statement? The variable y is a function of variable x. While we can fix x to belong to the real line corresponding to the physical world we encounter, we cannot be sure which values y will assume. This procedure of relating a quantity y to the real line x opens up possibility of things going crazy. All this nicely relates to what Richard Feynman described as the god playing a great game of chess. We as observers can only figure out the rules by watching it. Every once in a while, a strange move like castling blows our minds and forces us to rewrite the directory of observed rules. Now we draw those relations for rational powers of x. For example, these curves draw y equals x raised power 0.5, 1.3, 2.8, and 3.7. Notice this circle where all the curves pass through the point 1, 1. On the other hand, we have a missing left half. Again, this is a very interesting result. Why is this left half missing? Because remember, we can write, for example, 1.3 as 13 by 10. Since there was no x raised to power 10 equals minus a in the fourth quadrant, so we do not have an x for which the 10th power of a negative number can be associated to a number. This results in the missing left half here. In the positive real line scenario, our left half was entirely missing, and the asymmetry was balanced by incorporating the missing half in the form of negative numbers. In the current situation, a simple left half already exists for integer powers of x, but this left half is empty for the fractional powers of x and hence incomplete. We will see how to complete this left half that gives rise to the concept of imaginary numbers. Now let us see this graph where we drew integer powers of x in a 2D drawing into a 3D setting. We can see x raised to power 0, x raised to power 1, x raised to power 2, and so on. Here we can see that all the curves pass through plus 1 at this point and oscillate between -1 plus 1 and -1 minus 1 between these 2 points. -1 raised to power 0 plus 1, -1 raised to power 1 minus 1, -1 raised to power 2 plus 1, -1 raised to power 3 minus 1, and so on. This oscillation or vibration is represented by the purple arrow. It is evident that plus 1 on the x-axis is a very dull number, does nothing noteworthy as an input to a function. On the other hand, -1 on the x-axis is a very exciting number as input to a function and heavily contributes towards the beauty of mathematics, signals, and our understanding of the universe. What can we infer from these oscillations for the fractional powers of x equals -1? If -1 raised to power 0 is plus 1 and -1 raised to power 1 is minus 1, then the fractional powers of -1 must lie somewhere between plus 1 and -1. However, they cannot lie on the y-axis because we already saw that the left half for the fractional powers is empty. This necessitates that we depart the 2D plane and enter into an imaginary dimension, much like platform 9 3/4 used for boarding the Hogwarts Express in the Harry Potter Wizarding World. The dashed rectangle drawn here points towards this imaginary dimension coming out of the page. The fractional powers of x must lie somewhere in this plane. Starting from -1 raised to power 0 at the top, the fractional powers of -1 must return to -1 raised to power 1 at the bottom to maintain continuity. This is indicated by this half triangle here. A journey from -1 raised to power 0 to -1 raised to power 1 also implies that the powers are uniformly distributed in this region. Just like when we devise a negative half, we threw the numbers in a uniform fashion. Here we are throwing those powers in a uniform manner. Summation of two such powers while forming a product should simply move in proportion to this sum. For example, -1 raised to power zero point 0.1 plus zero point 0.2, which is -1 raised to power zero point 0.3. We conclude that -1 raised to power zero point 0.5 should lie on the corner of this triangle because zero point 0.5 lies between 0 and 1. This is perpendicular to both x-axis and y-axis lines and represents the third dimension. Owing to the properties of unity, the distance of each such point from -1, 0 must be 1, that is its length or magnitude. This implies that the fractional powers of -1 can lie neither on the rectangle nor on the triangle, because the lengths of all such points as measured from -1, 0 will not be equal to 1. In which shape do all the points lie at an equal distance from its center? Yes, this must be a circle. This leads to the fractional powers of -1 lying on a circle in an imaginary dimension similar to a clock, as shown here. If the powers of -1 are uniformly distributed in a circle in this 2D plane, what else is uniformly distributed in a two-dimensional plane? It is the angles. We conclude that the powers of -1 correspond to the angles across the unit circle, and we can write the expressions -1 raised to power 0 equals 0 radians, minus 1 raised to power 0.5 equals 90 degrees, or pi by 2 radians, minus 1 raised to power 1 is 180 degrees, and minus 1 raised to power 1.5 is 270 degrees. Since minus 1 raised to power 0.5 lies on the perpendicular axis due to 0.5 located exactly between 0 and 1, it is a rotation of the number minus 1 raised to power 0 by 90 degrees in this 2D plane. A more important implication of this perpendicularity is that we choose minus 1 raised to power zero point 0.5 as the representative member of this third dimension and give it a specific name, I. Minus 1 raised to power zero point 0.5 equals I. Notice the difference between this expression where I is situated on the right side with conventional description of imaginary numbers where I is situated on the left side of the statement I equals square root of minus 1. While this difference seems little, it translates into a huge gap as far as the grasping of the idea of imaginary and complex numbers is concerned. The former is assigning a notation I to a number minus 1 raised to power zero point 0.5 we have already become familiar with, while the latter is traditionally used to assign a value square root of minus 1 to a notation I introduced without any justification. So here I have answered question number 1 at the start of this video. What is the role of number square root of minus 1? What sets it apart from other impossible numbers, for example, a number k such that absolute value of k equals minus 1? I hope that this has become clear now. With this understanding, we can locate any integer power of minus 1 by traversing a path along the unit circle. So minus 1 raised to power zero point 0.5 is I, minus 1 raised to power zero point 0.5 times 2, which is I square, is I times I. So I times I, which will be minus 1 raised to power 1 and minus 1, or 180 degrees. I cube will be another 90 degrees rotation, so it would be a negative I. Two ways to see this result. One is I cube can be written as I square times I, but I square equals minus 1, so that would be minus I. The other would be minus 1 raised to power 3 times zero point 0.5, which would be 1.5, which is 1 and zero point 0.5, and this is minus 1, this is I, so we have minus I. If we associate the idea of I with the 90-degree rotation as we have, then 90 I, then another I 90, another I 90. After 4 such rotations, we come back to the number 1. There are two changes I have incorporated into this figure. As compared to our original 3D figure, we have now moved the camera to the right side. We are looking at this figure from this angle now, and this is the real axis. This one is the imaginary axis which is coming out of the plane. The second is that initially I put the starting angle 0 at the top to correspond to this figure here. But now I am bringing the angle 0 to the right side so that to conform to what we normally use in mathematics. However, I have given the name YR and YI to them, not X and Y. Now we can generalize the relationships between the powers of minus 1 and angles on a unit circle. For example, if you enter the expression minus 1 raised to power zero point 0.1 in Wolfram Alpha or some other computational engine, the answer you will get will be equal to 0.95 plus zero point 0.3 I. But how? In the simple approach through which we have come to complex numbers, we can see that a rotation of 90 degree is minus 1 raised to power zero point 0.5. So zero point 0.5 to 90 degrees, zero point 1 to what? 90 times zero point 0.1 over zero point 0.5, which is 18 degrees. And the magnitude is obviously 1. As an extension, all multiples of zero point 0.1 correspond to multiples of 18 degree. 18 degrees minus 1 raised to power zero point 0.1. Minus 1 raised to power zero point 0.2, 36 degree. Minus 1 raised to power zero point 0.3, 54 degrees. Minus 1 raised to power zero point 0.4, 72 degrees, and so on. In such a setup, we will have a summation of powers correspond to the summation of angles. So minus 1 raised to power zero point 0.2 plus zero point 0.3 is the same as 36 plus 54 degrees. That is how we move along the unit circle. Either in minus 1 powers or in angles, both are the same thing. Let us now summarize a great mental shift one experiences in understanding of imaginary numbers. When you tell someone the natural numbers are real, You can show them the phone you have in your hand, that is quantity 1. To prove that rational numbers exist, you can divide an orange into two halves. To show them the irrational numbers, you can always point towards a circle or a triangle. But if someone ever tells you that imaginary numbers are real, ask them to show you something that contains imaginary numbers. In reality, you will never encounter imaginary numbers in the real world. The great mental shift is as follows. This x-axis real line corresponds to the physical objects we encounter in the real world. However, nothing can be said about the y-axis real line. The mapping from x to y, which came from our polynomial expressions, opens up the possibilities of discovering unknown quantities, which can be crazy, like imaginary, complex, figurative, convoluted, any kinds of numbers can be invented from that mapping. This is in the nature of the problem. If you land on moon LV 426, you will run into xenomorph like this instead of cute cats like on planet Earth. This also tells us that the confusion regarding square root of -1 and complex numbers is not due to an intellectual limitation of ordinary people. It is due to the way complex numbers are introduced by the masters. What they do is that they introduce the complex numbers as z equals x plus iy. The blue plane you can see here. The real line is here, the imaginary line is here. Such an introduction implies that a complex number xy is just one further extension to a real number x by including a square root -1 on the vertical axis. A difficult concept to wrap your mind around. This is where one wonders what is so special about square root of -1 that leads to devising a completely new category of numbers and placing square root -1 on a perpendicular axis. In this alternative approach, a complex number then is a point in a 2D plane formed by a real axis yr and an imaginary axis yi, such that the point z equals -1 raised to power 0 times yr plus -1 raised to power zero point 0.5 times yi. So 1 times yr plus I times yi. Here it is clear that the real line corresponding to the physical world is here. The y real line multiple of -1 raised to power 0 and multiple of -1 raised to power 1 appears here, and the rotations that appear due to the reasons discussed before, we have a multiple of -1 raised to power zero point 0.5 along this axis, because I is simply a rotation of 90 degree from here to here as discussed before. Otherwise, power zero point 0.5 of -1 is not special in any other aspect. I feel a particular appreciation for this inclusion of -1 raised to power 0 with the real part and -1 raised to power zero point 0.5 with the imaginary part, because such a representation lays bare the whole concept of complex numbers right in the notation itself. If you have this equation, not this one, and this graph, it is enough to understand what complex numbers are all about. YR and YI also tell us that the real line YR came into being through operations on x-axis real line, and then functions involving powers gave rise to yi dimension. We are now ready to draw the missing left half plane for the fractional powers of x. So we start with the graph of y equals x raised to power zero point 0.5 for both positive and negative values of x. You are already familiar with the positive y values for the positive x values for y equals under root x or y is equal x raised to power zero point 0.5. We have seen this many times before. To draw the negative half, let us assume that x equals minus zero point 0.3. X equals minus zero point 0.3. Then we have minus zero point 0.3 raised to power zero point 0.5 equals minus 1 times zero point 0.3 raised to power zero point 0.5, which is equal to minus 1 raised to power zero point 0.5 times zero point 0.3 raised to power zero point 0.5. Now we know that zero point 0.3 raised to power zero point 0.5 is a number equal to 0.548, while minus 1 raised to power zero point 0.5 is simply a rotation of 90 degrees. Consequently, we mark the point minus zero point 0.3 raised to power zero point 0.5 with the same value as zero point 0.3 raised to power zero point 0.5. but at a 90-degree root angle from YR, the real YR, at x equals minus zero point 0.3. That is shown with the green square here. The conventional way to write such a point is z equals 0.548 I. I prefer to write it as x equals minus zero point 0.3, yr equals 0, and yi equals 0.548. Repeating the same procedure for many other negative values of x gives us the negative half of y equals under root x, which is given by this red line. Now the complete graph is given by the blue line for the positive x values, the red curve for the negative x values. This circle is drawn at x equals minus 1 to show that this point is given by minus 1 raised to power 0, minus 1 raised to power zero point 0.5 or 90 degrees, minus 1 raised to power 1 or 180 degrees, minus 1 raised to power 1.5 or 270 degrees. Unlike the conventional graphical representation of y equals x raised to power zero point 0.5 that leaves the left half empty, here we have introduced an imaginary axis out of the page that has an exactly similar negative half. When we do this for all negative values of x, these two graphs are very similar, but the left half is bent at an angle of 90 degrees. That is why this curve cuts the blue dot minus 1 raised to power zero point 0.5 at x equals minus 1. I find this figure very beautiful. Now we have become able to generate any fractional powers through the following algorithm. Choose a negative value of x, and x raised to power f is given by minus 1 times mod x raised to power f. We divide it into two parts. One is minus 1 raised to power f, and the other is the positive value raised to power f. The magnitude is given by this part, and the angle is given by this part. For example, suppose we draw y is equal to x raised to power zero point 0.2. We already know that x raised to power zero point 0.2 is given by a particular curve on the positive x-axis. I am showing this picture from a very narrow camera angle so that we can see the angles departing away from the positive real line. Minus 1 raised to power zero point 0.2 times mod x raised to power zero point 0.2. This graph, although it is not clear right now, but it will be clear soon in the next slide, is a mirror image of this y equals x raised to power zero point 0.2 graph. There is no difference between these two. But the only difference is that this curve is departing at an angle of minus 1 raised to power zero point 0.2, which is equal to 36 degrees from the positive real line. Why 36 degrees? Because minus 1 raised to power zero point 0.2 we have found out before is equal to 36 degrees. The same can be said about minus 1 raised to power zero point 0.7, which is 126 degrees, and minus 1 raised to power 1.3, which is 234 degrees. To sum it up, the fractional powers of x equals 0.25, zero point 0.5, 0.75, 1.0, 1.25, and 1.5 are arranged in a circle in the plots of this figure. To set our reference, observe that the red curve for y equals x raised to power zero point 0.5 is the same as we saw before, while the orange line is the familiar y equals x or y equals x raised to power 1 graph. All the graphs are located at angles corresponding to their own powers of minus 1 and are uniformly spread across the unit circle because I chose them as multiples of 0.25. When you trace them from here, 0.25, 0.5, 0.75, 1, 1.25, 1.5, you will see them. They are all cutting through the orange unit circle in a counterclockwise manner. This image is really delightful. The next step is to form the magnitude plots depicting this beautiful symmetry. Compare the colors of the curves in this figure with the curves in this figure. Light blue, and so on, green, green. Since this is a magnitude plot, the angle information is suppressed. All of these curves without any angle map back to this 2D plane, which is here. What do we see here? They become symmetric. I find this symmetry arising from our own choice of numbers quite extraordinary. The negative half here complements the positive half in a similar manner as the negative half on the x-axis complements the positive half in the case of negative numbers. That is why we can say the same sentences we say about the negative numbers. That is, to cater for the corner case where fractional powers of x are only defined for the positive half, an innovation in the form of imaginary numbers was introduced by assigning an angle as a power of -1 in an extra dimension to a real number. And so imaginary numbers made it possible to establish symmetrical counterparts to fractional powers of positive x on the same plane. So that is how complex numbers came into being. For a PDF version of this guide and other topics, you can visit my website wirelesspy.com. I will also provide the link below. If you like this video, you can share it and comment below.